Okay, so the concepts that you need to be able to understand or to define here. First, a conjecture. A conjecture is an educated guess, which is just basically an unproven statement. And it'll generally be based on observations. When you start a proof, which we will get into later in this chapter, it begins with a conjecture. Like it begins with an end state that you're looking to prove, but until it's proven, it is just this. It's based on some observation. It's what you're looking to demonstrate, but again, it's an educated guess in that regard. Inductive reasoning versus deductive reasoning. We'll talk about the difference between those two in this section. But inductive reasoning is just drawing conclusions from patterns that you recognize. So inductive reasoning is just making an inference, and seeing a pattern and trying to guess what are the rules that govern that pattern. And so it'll be based on intuition, and generally this is kind of how the observations begin. Okay? So you look at a pattern, you make an observation, and draw a conclusion or draw a conjecture from what you see. Okay, so the types of inductive reasoning that you're going to see in this section are sort of like logic puzzles. Okay, it's going to ask you to recognize patterns that you notice in sets of numbers and letters and diagrams. So if you look at this pattern of numbers right here, okay, what would you guess is the next number in this sequence based on what you see moving from term to term? And see if you can identify that on your own. Lots of the inductive reasoning types of patterns are based on counting. Okay, so often it's a good idea to just see if you count from one to the next, especially if you see an order, right? In this one, we're going from lower numbers, and as you move to the right, they're getting bigger and bigger. So let's see like the counting principles involved in them. So for moving from the first term to the second, we add 18. From 18 to 37, we add what? 19. From 37 to 57, we add. Are you starting to see the pattern? Yeah, the next one we add 21, we add 22. And so to get our next term, what are we going to have to add to 100? Yeah, so that is using inductive reasoning. So you get 123 as your answer. That's the pattern you recognize from what's going on with that, the sequence of terms. So a lot of times it'll be based on just counting. Now, sometimes it'll also be based on using a diagram. And in that diagram, again, counting principles will likely come into play. But see if you can find, based on what you see in this second problem right below, okay, how many triangles are going to be in the eighth figure based on what you see right here. So this is first figure, second figure, third figure, and moving on from there. You want to find what about the eighth figure. And so see if you can find what that would be. How many of you drew a figure that represented the eighth figure? Okay, so one of the ways to solve this is just to draw out what you see. So if you notice here, figure 1 has one square with triangles on each side. Figure 2 has 2 consecutive squares with triangles on the outside. 3 has 3 consecutive squares. So you could draw 8 consecutive squares, draw the triangles on the outside, and count them up. Ideally, you notice a pattern before you go through that process. But if you do need to draw it to figure it out, that's fine. And that is one of the strategies. What you can kind of see here, though, is when you look at these, you have 1, 2, 3 triangles. Well, 3 squares that correspond to this number right here. Each of those 3 squares has how many triangles on it? Each has 2, right? So what you have right here is you have, in this case, you have 3 times 2, right? 3 squares have 2 triangles. Plus, you also have these triangles on the side here. So you're adding the 2 triangles on the side. So this gives you the total number of triangles here, right? 3 times 2 plus 2. So this has 8 triangles. If you look at that pattern right here, you can go to 8. You have 8 squares with 2 triangles each. Plus you have the 2 triangles on the outside. And so your answer can be calculated using that process. 8 times 2 is 16, plus 2 is 18. So that's sort of the process that you're looking to use when you make these inferences and when you use this inductive reasoning. Okay. Can you draw a conclusion based on a pattern you recognize from the specific, these 3 examples, to the general, which is this rule, kind of this formula-based relationship here? All right, see if you can extend that idea to this next question here. Can you find out how many total blocks will be on a structure that has 10 layers as you continue this pattern? So remember, your answers can have calculations. So in this particular problem, I would enter my answer as a calculation. Okay, as I walk around, I see a number of you noticed the pattern and answered the question slightly wrong, just because it's asking for the total number of blocks, not just how many blocks are in the 10th layer. Okay, so if you look at this, what you're seeing here is layer 1 is a 1 by 1, right? It's 1 block. Layer 2 has 2 blocks by 2 blocks, 3 blocks by 3 blocks, 4 blocks by 4 blocks. So the layer is telling you that this square is formed like 4 by 4. So the next one's going to be 5 by 5 or have 25 blocks. So again, when I saw, a lot of you have the pattern, right? The 10th layer is going to have how many blocks? This is 1 squared, 2 squared, 3 squared, 4 squared, and so on. So you have 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, right? Now, that's a lot of numbers. Okay? However, because you can enter a calculation, you can just enter it right here, right? 1 plus 2 squared is 4, 3 squared, 9, 4 squared, 16, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared. So that is your answer. I would enter it just as that calculation. And when you get it, the preview will show the answer, which is 385. And that would be your solution. Okay, but the pattern is, again, recognizing that each layer represents a square with those dimensions, 1 by 1, 2 by 2, 3 by 3. Okay, now, if you answered 100, which is probably the most common missed answer on this, there is another version of this question that will ask specifically a structure, this structure, or in this structure, how many blocks are in the 10th layer? And so there is a different version of this question that actually asks that problem. But this one wants the total number, and so the total is the combination of all of the blocks added together. Be aware of that. Make sure that you have the correct version of that question when you enter your answer, that you're not just labeling the number of blocks in the layer, but the total. Or if it's just asking you for the number in the layer, you're not putting in the total. Okay, but that is the pattern that would give you your solution. All right, the last example here, I want you to try this on your own, please. Okay, can you find what the sum of the first 21 positive even numbers? When you're working through these problems, not everyone enjoys sort of these logic puzzles. Okay, that are inductive reasoning type of problems. And if you are having a hard time with them, use the try similar question. Try to see all the different possibilities of each like pool of questions that you come across. There's detailed solutions that describe the patterns. And just the more you're exposed to those, the more likely you'll be able to answer the questions when you get quizzed or tested on it. And so even if you don't like it, you might just have to be exposed to it a little bit more to try to figure out those patterns. And this is a small part of the overall, so if this gives you troubles, just like proofs, this whole chapter here is some stuff that it's somewhat more challenging than what students are used to seeing. So if this happens to be the case for these, give it your best shot, view a lot of the different similar questions so you can expose to all the different possibilities. All right, the process for this is to, again, recognize the patterns that are that you can observe from here. So this is the first positive integer, this is the second, this is the third, the fourth, the sum of the fifth. So you can see that those numbers are mirrored right here. This is n, where n is the number that you have. And then notice what n is being multiplied by. N is being multiplied by what in terms of n? N plus 1, right? It's the next consecutive integer. So your answer is the number times the next number, the number plus 1. So if you are looking for the first 21, then your n value is going to be 21, and you're going to multiply that by n plus 1, which is 22. So this would give you your solution if you recognize the pattern. Again, you don't have to try to count 21 of these instances and then manually count them. And you're looking for patterns and making a prediction based on that. So here, when you calculate this, you would get 462 for your answer, and that would be the solution. But once again, you can enter your answer as a calculation if you see that pattern. All right, so in the 2.2 material, some of the questions are going to be these inductive reasoning problems. Okay, find the pattern based on what you see. Okay, we've seen this word. This word showed up in 2.1. We're going to define it more specifically here. But counterexample is going to be a specific case where conjecture is false. Okay, so if you have a statement or a property and then you see an instance where that is not true, okay, that's an example, or that is what a counterexample is. Okay, so I want you to see if you can find from the 4 options given here, which is a counterexample to show that any number divisible by 4 is also divisible by 12 is a false conjecture. Okay, so you're looking for which of these numbers, 16, 60, 36, or 12, is divisible by 4 but not divisible by 12, right? So that's what you're looking for, the counterexample to that, and which number would that be? 16 is not divisible by 12, and so that would be your solution. Every other number there is divisible by both 12 and 4. Well, again, if anything is divisible by 12, then it's also divisible by 4. And so you're just looking for the one that disproves that conjecture. All right. So the inductive reasoning is that, looking for patterns. Deductive reasoning is going to be a little bit more formal relationship. And so the definition for deductive reasoning is to draw conclusions, now not from specific to general, but from general to specific. And it's based on concrete things like facts, definitions, accepted properties, theorems, laws of logic, and so on. So deductive reasoning is what we will be using for our proofs when we get into proofs again later in this chapter. And so when you're looking at these, you are testing to see, can you verify a statement based on either facts, definitions, accepted properties, which can include postulates, or proven theorems, laws of logic, which are axioms. All of those are acceptable justifications for proving a conclusion. So see if you can answer these two questions, part A and part B here. Given is the logic valid for those statements? Can you draw a conclusion based on what's provided versus what you know about the definitions and so on? So basically, when you're checking this, you're looking to see, can you find a counterexample to what it's the conclusion being drawn here? And so an acute angle is less than 90 degrees, and that's a definition. That's something that is accepted as a justification. It says, therefore, a non-acute angle is more than 90. Well, if you can find a counterexample, then it's not necessarily a valid conclusion. If you can't find any counterexamples, then it is a valid conclusion. So when we look at this, is there a counterexample to this final statement? Is there a non-acute angle that is more than, is a non-acute angle have to be more than 90 degrees? If it's obtuse, that would be more, right? Are there any other non-acute angles that we classified? The other classification is straight. So a straight would be an example. What's the other classification between acute and obtuse? Right. Is a right angle more than 90? No, it's exactly equal to 90, right? So a counter example is that a right angle is equal to 90. That one invalidates this statement. It's no longer true because there is a non-right angle that is not more than 90 degrees. So we found a counterexample to that. The right angle is that counterexample. Okay. For the second instance, we kind of look at the same thing. Can we find a counterexample of this? Okay. So when we look for this statement, if WXYZ is a rectangle, then its opposite sides are congruent. Okay. So if we kind of look at what we have here, a rectangle here, opposite sides are congruent. So that's the given, and that's a property of rectangles. Okay. The next part says, or the opposite sides of WXYZ are congruent, therefore it is a rectangle. Okay. Is there a way that we can demonstrate that any figure where the opposite sides are congruent, that it is not a rectangle? Any other figures that have that property? Yes, right? What kind of figure is this? It's a parallelogram. Okay, a parallelogram also has opposite sides that are equal, but it's not necessarily a rectangle. So once again, we were able to invalidate that conclusion. We found a counterexample. Therefore, this is not necessarily true. This last one is based on this property called the law of syllogism. The law of syllogism states the following. Okay, so if condition P, then Q, if that is a conclusion, and if Q, then R, then you can draw the conclusion, therefore, if P, then R. So notice that the way that these are related looks like this. If P, then Q. If Q, then R. This symbol with the three dots kind of in the form of a triangle means therefore. P is R. P leads directly to R. So we will talk about this again. This kind of mimics what's called the transitive property in the rules of logic. Okay, so if 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 one thing leads to a conclusion that leads to another conclusion, then it progresses from P all the way to R. Okay, so based on that relationship, see if this final set of givens is that conjecture, is that the assumed or educated guess there, is that true or not true based on that pattern? If we kind of label what we have, right? So if a figure is a square, that's P, then it is a rectangle, that's Q. If a figure is a rectangle, that's Q, then it has 4 right angles, we'll call that R. So there is the relationship. Okay, so is the conjecture stating that if P, then R? If the figure is a square, that's P, then it has 4 right angles, that's R. Does that follow that law of syllogism? Yes. And once again, very minor, you're going to see it in an example similar to these. Okay? That's all you'll need to know about this relationship. All right, so that's all of 2.2. Okay, 2.3 is just a single slide with several examples. And so I'm going to just talk through those examples, and then I'll give you the rest of class time to work. All right, so 2.3 is just going to be postulates that are kind of related to constructions, lines, and planes. Okay, and so the illustration is already provided for you. All we're going to write down is basically the conclusion, right, to complete the postulate. Okay, so the 2-point postulate states that through any 2 points there exists exactly one line. Okay, so if given points A and B, there's only one line here, L, that passes through them. Okay, that same diagram can be used to justify the line point postulate, which says that a line contains at least 2 points. Okay, now obviously a line contains an infinite number of points, but it needs 2 points minimally to kind of designate that line. So this is why we use 2 points to name the line. If you have intersecting lines, if 2 lines intersect, then their intersection is exactly 1 point. Okay, lines can't curve back around and cross each other a second time. Okay, so if 2 straight lines intersect, their intersection is going to be exactly 1 point. Okay, the 3-point postulate, as you can see right here, is that through any 3 non-collinear points, there exists exactly 1 plane. And thus we name the plane using 3 non-collinear points. And so a plane contains at least, same relationship, at least 3 non-collinear points. Okay, the plane line postulate, if 2 points lie in a plane, then the line containing them lies in that plane as well. And then finally, if 2 planes intersect, then their intersection is a line.